So today I thought we would go back and look at limits again. It's been since the beginning of the year that we looked at limits. You remember when we did limits, sometimes they were very easy. If you wanted to see where the function x squared was approaching as x approaches 3, we just went 3 squared and got 9. It was that easy. The problem came when we went to plug a into a numerator and a denominator, and you got an indeterminate form. If the numerator and denominator were both approaching 0 or both approaching plus or minus infinity, then we got an indeterminate form because it depends on how fast the numerator and denominator are approaching 0 or infinity that's going to determine your answer. That's why we call them indeterminate. So we're going to try to come up with another way of doing that. Before we had to do some fancy algebra, or sometimes we even had to give up because we couldn't figure out a way of doing it. So we've learned some things since then, and that's why we wait till now to explain this. So say you go to take the limit as x approaches a, and you get an indeterminate form, the numerator and denominator. So right now, what I'm going to do is just a proof. So just kind of follow. If I have f prime of a over g prime of a, we now have these formulas that we've determined for derivatives. So f prime of a is the limit as x approaches a of f of x minus f of a over x minus a, and the same thing down here for g of x. And since limits are our friends, we can say the limit of this function divided by the limit of this function is the limit of this function divided by this function. And when you divide this function by this function, the x minus a's cancel out, and you get that. And that's as far as you can go, but right now we're going to make an assumption. We're going to assume that f of a and g of a are both equal to 0. So that's an assumption in this proof. If we make that assumption, then we can just cross f of a and g of a out, and we're left with what we've got. So now we can make a theorem or a rule. Forget about the in-between part here. We can say if the assumption is true, if f of a equals g of a equals 0, then this limit right here, the limit as x approaches a of f of x over g of x equals f prime of a right here over g prime of a. If this equals this, then this equals this. It doesn't matter the order we put it. So this is one form of L'Hopital's rule. So L'Hopital was a French mathematician in the late 1600s. He died in the early 1700s. And his name was Guillaume François Antoine Marquis de L'Hopital. So we'll just refer to him as L'Hopital. And he actually spelled his name like hospital, Hospital. But the French language has changed somewhat since then, where they dropped the S and put an accent circumflex over the O. So I like this form better, so we're going to call him L'Hopital. And the interesting thing is, he didn't actually come up with this rule. he wrote a book in the late 1600s. It's one of the first books ever written about calculus, about infinitesimal calculus, and his friend, Johann Bernoulli, which actually was Swiss, and the Bernoulli family is really considered the most famous family of mathematicians that ever lived. Anyway, Johann was the one who actually came up with it, but L'Hopital published it in this book, and so he's given credit to this rule. So, to make it a slight bit stronger, what happens if f prime of a and g prime of a still turn out to be 0 over 0? Then what we do is just do it over again. Since they both would be functions and they both would satisfy this, we could say, we could take the derivatives and use L'Hopital's rule again. So to make it slightly stronger, we're going to say the same thing. If f of a equals g of a equals 0, then the limit as x approaches a of f of x over g of x equals the limit as x approaches a of f prime of x over g prime of x. So if this really does turn out to be a number, you can just stop at that point, but if it doesn't, you can just continue again and say this would be f double prime of a over g double prime of a. Or you can do the limit again. So this is the slightly stronger version of L'Hopital's rule, and that's the only one that I'm going to prove to you. But they went ahead, Johann, I assume, was the one who did it. He said this is not only true if they both equal 0, like 0 over 0, but also if they equal plus or minus infinity. Either plus infinity over negative infinity or plus over plus, it doesn't matter. And they also went on to prove, or one of them did, that it also works not just as x approaches a, but if x approaches plus or minus infinity. It doesn't have to just approach a number, it can approach infinity. So anyway, pretty important rule. So let's give an example here. The limit as x approaches infinity. Well, when you plug this in, you get infinity over negative infinity. Now, you can now use L'Hopital's rule, and it works out better, I've found, if you yell out, as soon as you take the limits and get that indeterminate form, yell out, L'Hopital! So, I just did it, so now I can use the rule. And I take the derivative of the numerator, 3x squared plus 2x, and the derivative of the denominator, 0 minus 9x squared. When I plug it in, I still get infinity over negative infinity. L'Hopital! So I take the derivative, 6x plus 2, the derivative of the denominator, minus 18x. I do it again. L'Hopital! I still get infinity over infinity. And finally, I get 6 over negative 18, or a negative 1/3. And I had so much fun. But, back in the third week of this class, we had another way of doing this problem. We said if you got a rational function, you could look at the highest power of x in the numerator and the highest power of x in the denominator and ignore everything else. We took an n behavior model, and then when they're both to the same power, we just looked at their coefficients. 1 divided by negative 3. Obviously a much easier way to do it. This way was more fun. So I'll let you pick the way you want to do it. Probably this is the way to do it in general. But there are going to be a lot of examples where we can't do it that way. They're not rational functions. So I'm going to give you some more examples over on this board. So the first one, when we plug in 8, we get 0 over 0. L'hôpital. So we take the derivative of x to the 1/3 and the derivative of x is 1. So we have the limit as x approaches infinity of 1 over 3x to the, it's not infinity, as x approaches 8 of 1 over 3x to the 2/3. Well, that's going to be 4. 8 to the 2/3 is 4, so you get 1/12. And I couldn't have done that problem with geometry. Okay, next one. The natural log of 1 is 0. 4 minus 4 is 0. L'hôpital. And I get 1 over x divided by, see, 4. And when I plug in 1, I get 1/4. So the derivative of the natural log of x was 1 over x. The derivative of 4x minus 4 was 4. Now when I plug it in, I get an answer. Let's try one that looks a little bit harder. 5x to the infinity. That's going to be infinity. Minus 2x is kind of inconsequential. E to the infinity is certainly infinity, even if you multiply it times 0.01. It's approaching a huge number. So, l'hôpital. Now, I get 20x cubed minus 2 over 0.01 e to the x. The derivative of e to the x is just e to the x, and the constant stays there. And the derivative of this constant, e to the 10th, is 0. So now I get infinity over infinity again. L'hôpital. So in the numerator, I get 60x squared. In the denominator, I keep getting the same thing. Now I could keep going farther, but what do you see? Eventually, this derivative is going to get down to 0. This is going to stay this same number, and x approaches infinity. This is going to go to infinity. So if the numerator is approaching 0, the denominator is approaching infinity, you're going to get 0. If you wanted to, you could just do a couple more l'hôpitals, but I think you can see that that's going to happen. Now, here's something quite different. We don't have a function divided by a function. We have a function times a function. And if we plug it in, negative infinity squared would go to infinity, and e to the negative infinity would go to 0. So this time we have infinity times 0. That's actually a different type of indeterminate form. If one number is approaching something huge, and the other number is approaching something really close to 0, when you multiply them, it's going to depend on how fast this one's going to infinity and how fast this one is going to 0. So again, it's indeterminate, but now we can't use L'Hopital's rule because it has to be in the form of a function divided by a function. But we want to use L'Hopital's rule. So what we do is we rewrite it. We write the numerator to be x squared and the denominator to be e to the minus x. Then 1 divided by e to the minus x is e to the x. So we haven't changed anything. And now we get infinity over infinity. Because e to the minus a negative infinity would be e to the infinity. So L'Hopital. Now we get 2x over, and the derivative of e to the minus x is e to the minus x times a negative 1. So now we get negative infinity over negative infinity. So L'Hopital again. And we get 2 in the numerator. And now we get just e to the minus x in the denominator. So as x approaches negative infinity, the denominator is going to get huge. The numerator is only 2. This one is going to approach 0. So a different type of indeterminate form that we were able to get into a form that we could use L'Hopital's rule for. Now this is one we did do earlier in the year, but it took about 10 minutes of a geometric proof to prove it because we couldn't do any algebra. But now, what do we get? Sine of 0 over 0. L'Hopital! And the derivative of the sine of x and the derivative of x, and the cosine of 0 is 1. So as x approaches 0, the sine of x over x approaches 1. And the reason that's true is because the function, the sine of x, and the y equals x, those two functions are so close to the same thing that they're approaching 0 at the same rate. And that's why their ratio gets close to 1. Okay, let's try 2 more. 0 over 0. L'Hopital. And the derivative of x is just 1. The derivative of x to the 1/2 is 1/2 x to the negative 1/2. So then you can just write that as 1 over 2 root x. So the numerator is 1, the denominator is getting to be really close to 0, so that whole thing is going to approach infinity. Now probably, to be really technically correct, you really can't approach 0 from both sides of the square root of x. It has to just be positive numbers, so I should have said from the right-hand side when I made up the problem originally. Okay, this last one, don't worry too much about it. It's kind of complicated, but it's really fun. So what do we have? We have the limit as x approaches infinity. Well, 1 over infinity would go to 0. So this whole inside the parentheses would go to 1, and then to the infinity power. So 1 to any power is 1, but remember, this doesn't quite get to 1. It's getting to be 0.999999999, but you're taking it to a huge power. So it's kind of interesting to see what the answer might be. Well, in order to do this problem, what you're going to have to do is let y equal that. But now we're going to take the natural log of both sides. And what we're going to do, instead of trying to find the limit as x approaches infinity of y, we're going to take the limit as x approaches infinity of the natural log of y. So we're going to just work on this problem instead. So I'm going to take the limit as x approaches infinity of this side, and the limit as x approaches infinity of this side. Now, on this side, what can I do? I can take that x out front. That's an exponent, so I can make it x times 1 plus 1 over x. Now, as x approaches infinity, this is going to go to infinity, and this is going to go to 1 plus 1 over something really close to 0. We can't use L'Hopital. But we can rewrite this. Write this to, oh, I missed the natural log of this. So this is going to infinity, and this is going to the natural log of 1. So you have like infinity times 0. Again, that's that indeterminate form. So I'm going to do this and rewrite this as the natural log of 1 plus 1 over x divided by, instead of times x, divided by 1 over x. Now we get the natural log of 1, or really close to it, so 0 divided by 0. Now we can do L'Hopital. And the derivative of the natural log of this is 1 over 1 plus 1 over x times the derivative of 1 plus 1 over x, which is minus 1 over x squared. And the derivative of 1 over x is the same thing, minus 1 over x squared. So now we can cancel this and this, and we're left with only 1 plus 1 over x. And as x approaches infinity, the 1 over x is going to approach 0, and you just get 1. But remember, that's not our answer. That's what, as x approaches infinity, the natural log of y is approaching 1. So y itself is going to approach e. So that's going to be our answer. The natural log of y is approaching 1. That means y, the natural log of e is equal to 1, so it's going to be approaching e. Now, why is that so exciting? Besides getting that to be our answer right there, we have a good way of approximating what e is. We can just pick a really big value of x, like 10,000. So if I did 1 plus 1 over 10,000 and did it to the 10,000th power, I'm going to get a good approximation for e. And if you put that on your calculator, you get 2.7181. In actuality, e is 2.7182 something. So and the bigger the value of x you pick, the closer you're going to get an approximation to e, that irrational number. So I'm hoping that you enjoyed that. Most of the problems you're going to see where you use L'Hopital's rule will be the other type of problem. So good. Have a good rest of your day.